So just how bad is climate change? Well, before we can make that determination, we have to understand a little bit about climate change. And we have to understand that, in fact, climate change is really a function of two things, two very strong greenhouse gases. It's a function of atmospheric CO2 as well as methane. And both are interconnected. Atmospheric CO2 at this point is well over 400 parts per million. I believe it's now sitting pretty strongly at about 404 parts per million. That's how CO2 is measured. It's measured in parts per million. So what we can see over time is it's going up and up and up every year. Now let's take a look at the last 400,000 years. We can see that it's gone up before in the past, you know. Take a look here, you know, it's almost like breathing. Here's a time of deep glaciation, and then it ends. And then it gets warmer again as the CO2 goes down. There's a time of deep glaciation, and quickly it toggles back and it ends. And it takes a long time to cool down again, and then there's a deep time of glaciation, and then it ends. It's almost toggling, right? It's breathing. It toggles between glaciation and non-glaciation. But take a look at this. That goes straight up. And we have not yet realized the warming that's going to be coming to us as a consequence of that. In fact, atmospheric CO2 levels are now hitting and exceeding concentrations that have not been seen since the Pliocene of 2 or 3 million years ago. That's fairly stunning. And as well, carbon dioxide levels are higher today than they have been for 20 million years. That's something that's quite notable, isn't it? So what are the dangerous levels? Well, I think we're already in a dangerous level, but James Lovelock, a notable scientist, predicted that at 450 parts per million, the ocean circulation actually stops. At 350 parts per million, which we have far passed, James Hansen wrote a paper that warming at this level will cause methane releases in the Arctic. And at 300 parts per million, well, we knew about the first signs of global warming as far back as 1950, and that's where it was at that time. So in any case, we're well into a critical time of CO2 emissions. But one more fact to take away. CO2 emissions take 10 years to reach the planet's peak heat. What this means is when you put a pot of water on the stove, it doesn't boil immediately. It takes some time. Likewise, CO2, after you emit it, it takes 10 years to actually realize that heating in the actual atmospheric temperature. CO2 does a deadly dance with methane and with temperature, and they all are interrelated. Generally speaking, the sequence of events is as follows. The CO2 gets emitted, the temperature goes up, the methane gets emitted, the temperature goes up some more, and then you get a lot of heat. Today we're going to be talking about feedbacks in the Arctic. There are a lot of climate systems that all work together in the ecology, and I'll just give you a few minutes to take a look at this very interesting chart. But in this talk today, we are going to be discussing and at least touching upon every single item in this chart that's marked in a blue box. So take a look at it. It's a fascinating thing how Earth systems work together. But to be sure, it all starts with emissions. So what's really the takeaway in this chart? The emissions box right here. This is us. We are putting the emissions into the air in terms of CO2. Everything spins out from that one box. If you'd like to find out more about feedbacks, please look at the work of David Wasdell at the Apollo Gaia Project at apollo-gaia.org. He is an expert in feedbacks of the climate. So kids, fasten your seatbelts. It's going to be a bumpy ride. The first thing that we're going to talk about today is not methane. The first thing we're going to talk about today is the polar jet streams. For polar jet stream work, please reference the work of Dr. Jennifer Hynes. She is the absolute expert in polar jet streams and has created a lot of videos that you can find on YouTube. So some basics about the jet streams, first of all. They are slowing down and they are becoming more wavy. They are circumnavigating the globe at a slower speed and along wavier tracks. And the waves are now more elongated, they're more stretched out vertically, which they shouldn't be. And because usually it's like a little ruffle around the top of the Earth, but it's not like that anymore. So now cold air can move down more easily from the Arctic, and consequently hot air can move more easily from the temperate zones squarely into the Arctic. So scientists have now evidenced that these persistent extreme weather patterns that we've been seeing around the world are increasing in their frequency due to rapid heating of the Arctic that's changing the behavior of the jet stream and in turn the polar vortex. This is fancy language that just means you get these weather patterns that can be strange and they stick around for a long time. Here's an example. Those of you in the United States, especially those of you in the eastern United States, may recall that last winter was absolutely brutal. I mean, in the Midwest, it was colder than it was on Mars. That's unbelievable. How could that be happening? I thought that we were like in a point of global warming, not global cooling. What's all this ice and snow and really inclement cold temperatures, and it hung around forever? Well, if you look at the map in front of you, you can see there's a big patch of purple. That's the United States and the East Coast. And that is actually the Arctic vortex that has been pushed out of the Arctic, split in half, and settled on the eastern United States and the Midwest. As well, you can see hot temperatures invading the Arctic up by Alaska and coming in. And if you look down, this is a temperature anomaly map, how much it's departed from average. You can see almost a blister of hotness. Look at this blister of hotness right through the Arctic, and then cold over here in Siberia, but really the significant cold is right here in the United States. And that's what we put up with this winter, and I'm sure many of you went through that. So that was the splitting of the polar vortex this last November. So to illustrate a few ideas, I'd like to do a couple of case studies, and this is actually going to illustrate the polar jet stream and it's changing right now. So this first case study has to do with the Alaskan heat wave that started in May. And in Alaska in May, it was primed for disaster. It had been since the 1930s, increasing on a trend of hotter and drier. And in fact, May 23rd found us at 91 degrees in Eagle, Alaska, and high 80s and 80s throughout the rest of Alaska. What in the world is going on that we have these high temperatures in Alaska? We'll take a look at this temperature anomaly map. So this map that you see here on the left is actually a temperature anomaly map. Look at Alaska. Alaska's red hot. I mean, it's not even just a little bit hot, it's like extremely hot over average. This is actual temperature, and even in actual temperature, look at this. It's much hotter than the other places, and you shouldn't have any red in Alaska in May. That's abnormal. And again, to illustrate the point, look at Fairbanks, look at Eagle. They're on fire. Clearly something is up in Alaska, but the story really is around the jet stream and how the jet stream reacted to the Alaskan heat wave. Please take a look at this. You've got here Alaska. I'm just drawing it out. So that's Alaska right there with the tail of Alaska, and here's Greenland for reference, right? So here's the jet stream. It's coming along very fast, and it hits this heat wave of Alaska, and it can't jump across, and it gets confused, and it basically is like, oh my God, I've got to follow the cold air. It tries to find the cold air, and it pushes a bunch of itself right up here squarely into the Arctic, then sort of jumps across, and it splits. I mean, this is the jet stream. The jet stream should be one contiguous flow, not a broken up mess like you see in front of you here. Now, the next day, you can see that it actually created a little stream that went all across the Arctic, and this is you know, air that's running like over 100 miles an hour in the jet stream, and it broke. So it broke in two. Right there, you can see it. And that's kind of how it adjusted the next day. So another case study. We're going to have another case study about the Russian heat wave just a little bit further on down in June, and show you how that wrecked the jet stream as well. We had a Russian heat wave that happened in June that put a lot of hot air into the Arctic, and here you can see the same thing happening. Just for reference, here is Greenland. You can see Greenland right there, but this is Russia under here, and again, the jet stream followed the hot air and mangled itself beyond all recognition, splitting up yet again. So let's take a look at one more case study at what happens with the jet stream here. You can see Europe in this case. Europe and Spain and France and everything is very, very hot in July as well. We can see some cold air poking in on each side. How does that manifest in the jet stream? You have these kind of dips that happen and eddies, and you know, it's pushing the jet stream in all sorts of different ways, but you can see the cold is coming down, the hot is going up, and these weather patterns tend to persist. One more heat wave, we had the Siberian heat wave in July, and it got up to nearly 100 degrees Fahrenheit, 37 degrees centigrade, extremely hot. Right here, here's Alaska just for orientation, and here's Siberia. This got to be very, very hot. And, you know, this is not normal to have 98 degrees Fahrenheit in Siberia. It doesn't really happen. So here's an interesting fact. While the media gives wide coverage to heat waves that have been hitting populous countries such as India, Pakistan, US, Spain, France, less attention is given to heat waves hitting the Arctic. But in truth, these heat waves hitting the Arctic have a huge effect on us. Take a look at how this particular heat wave up here in Siberia mangled the jet stream once again. See, it's coming along here, it breaks, it goes up into the heat wave, and then across the Arctic. So the point of this is that the jet stream at this point is very, very mangled, and it's not acting anything like it used to do.